Thanks for the introduction. Yeah, so my talk today is I'm going to go into a little bit more about testing needs. And my focus is on validation myself right now. And so the talk is going to address what are our testing needs to validate the tools that Jason's talking about. So we have these modeling tools. We want to be able to design our system. We want to be able to optimize our system. But to be able to do that, we really need to have tools that we trust and tools that are verified and validated. So yeah, this is the overview here. Accurate and robust modeling tools are needed to be able to investigate and develop new offshore wind designs. And to investigate these designs, we need to make sure, really that our tools are acting as they're supposed to be. So the way we assess the accuracy, make sure they're working as they need to be, is through verification and validation. And the thing that I'd really like to emphasize is once again the need for public information. In order to really do validation effectively, we really need a lot of open models, open information to be able to do this validation, open test data. And one of the great examples that we have for land-based wind is the NASA Ames test, which I assume a lot of you here are familiar with. And it's also one of the very few tests that's openly available, but because of that, it's been used extensively throughout the years to improve and validate the land-based modeling tools. So it'd be great to have things like that also for offshore wind so that we can do validation as well. I'm going to skip over that slide. So I want to just give a little bit of background of what verification is versus validation. We talk about verification and validation a lot. And the way I view verification is that verification is really just the assurance that your modeling tool is working as you think it should be. So you've chosen a modeling theory, you've implemented it in your tool. Have you implemented it correctly? And we've had some projects that have looked at verification of modeling tools. Sorry. Wrong slide. we've had some projects that looked at the verification modeling tools, and these are ones that are run under some IEA research tasks. Some of you may have heard of the OC3 and OC4 projects. OC3 standing for the Offshore Code Comparison Collaboration, and OC4 adding a C for continued. So these projects really sought to verify the tools, trying to see if they're working as they should be by comparing simulations from one modeling tool to simulations from another modeling tool. But that verification doesn't really tell you, okay, we can see that it's acting as we think it should be, but is it really representing the real world behavior of floating offshore wind turbines correctly? In order to assess that, you need to move to having a set of data to compare to. So validation is really then the assessment of the accuracy of a modeling tool and representing the real world measured behavior of a physical system. And obviously to do this, we need test data. So an offshore wind modeling tool can be validated for a specific type of system such as a spar, TLP, or semi, but to understand if it can be used for a variety of systems and to be able to create new types of floating offshore wind systems, we need to really validate it for an array of types of systems, as well as a lot of different environmental conditions and a lot of different types of tests. So tests such as ones at a component level, as well as scaled tank testing and full-scale open ocean testing, because all these different types of tests really pinpoint and focus on different parts of the tool for validation. And as I mentioned, publicly available data sets are really the best because then we can have a lot of different modelers looking at their modeling tools against the same type of validation data. So we can really see the differences between the different modeling approaches and what is the most effective. So here I put together a slide of really what I see as the model validation process. I don't want to go through all the steps, but I did want to point out some of the steps that I think are really lacking in the data that we are working with presently. The first is that ideally it'd be best to have, rather than just obtaining a data set from some party to do validation with for your tool, it'd be great to actually have the modelers, the validators being part of that testing process. And having that testing process actually have specific defined objectives for what you're trying to achieve. So for instance, if you're trying to look at, how does the floating turbine behave when it moves through a wake condition, you can develop tests that are specific to answering that question and validating the capability of the tool in that situation. The other areas that I think are lacking is that there's not a lot of quality checks done on this data until the very end. You're getting this data set that can have perhaps really poor quality, and you don't understand that quality. And unless you're involved in the test, you can't really do a good assessment of how good the data is. And then uncertainty. Once again, you're obtaining these data sets and you're doing comparisons, and how can you really say how well a modeling tool is representing real-world behavior unless you have some bounds on what that measurement, the uncertainty in that measurement actually is. So without doing these quality checks, without doing uncertainty, you really can't do an effective model validation. So as I mentioned previously, there's 3 different types of data that really can be used for validation, which I show here. Data from component level tests, and then full system tests either done at scale sized or full scale in the open ocean. And each of these approaches has their advantages and disadvantages, which I'm going to go over. And ideally, if you really want to, as I said, validate a modeling tool, you really need data from all these different types. So component level testing is the examination of just a part of the system, not the complete coupled wind system, but just a subset or unit of this. And the purpose of the component level testing is really to try to focus on a certain aspect of the system to better understand the fundamental physics of it. So examples could be if you want to look at just the behavior of a single blade or just a single member in the flow to better represent what the aerodynamics and hydrodynamics are on that member before you incorporate it into the full system. But it can also be a combination of components where you're looking at things like when you put 2 cylinders together, how do the hydrodynamics interact then? And if you have multiple cylinders, obviously you have shadowing effects just like you do for multiple turbines. And so you can do tests that really focus on trying to understand those behaviors better. I've also listed at the bottom of these slides some of the data that's presently available out there in the public for us to use, which we can see is fairly limited. There's the project OC5, which I'm helping lead, which is focusing on trying to validate offshore wind modeling tools. And we've been looking at 2 data sets that we've been able to find in the public, one from Marintech and one from DTU, DHI, which are basically looking at fixed cylinders in a basin. And you may say, oh, well, there's been lots of tests of fixed cylinders and basins over the years. Well, with offshore wind systems and with any specific system, those properties of the cylinders may change. A lot of the fixed cylinder tests that have been done over the years assume an infinite cylinder and an infinite depth water, but here we have cylinders that are piercing the water, ones that are very shallow, ones that are fat, and the properties change how the hydrodynamics are going to look on those systems. So looking at, so then we want to look at the full system. We don't just need to look at components, we also want to look at the full system. And you can do that in a scaled setting in a tank where you have a really controlled environment, or you can look at a full-scale system out in the open ocean. And some of the advantages of doing scale testing is, one, it's obviously more affordable than building a full-scale system. You can really prescribe the conditions yourself. You know what they are very well. And you can also do a lot of measurements to assess what's happening on the system and in the environment. You can also examine the system in extreme conditions because you can apply the wind and waves such that an extreme condition happens. If you're out in the open ocean, you have to just wait for it to happen. And you can also do a stepped approach, which is very beneficial to look at how the system responds for specific types of excitation. So you can look at the wind and waves separately. And you also probably have less uncertainty in the tank because you're doing a lot of the prescription yourself and you can better understand it. The disadvantages are, though, that there's scaling issues, which we've seen numerous times. So it's a conflict between Froude and Reynolds number being scaled simultaneously. You also are constricted to the limit of the range of conditions in the facility. You're also constricted to the size of the facility, so your scaling is based on what can fit in that facility. Also, because you're at a scaled size, your measurement equipment, unless you do a really good job, in general is going to be very large compared to the size of your system, so it's also going to influence the behavior of your system if you have really bulky sensors and measurement devices. And as the deep sea wind project is seeing, it's difficult to scale the turbine, and it's so far been really difficult to scale the controller effectively in a tank setting. So in terms of data availability, really the deep sea wind project had this focus of trying to get some of this this validation out there to the public, and they did some really great tests both in 2011 and 2013. In 2011, they looked at a TLP, spar, and semi. In 2013, they retested that semi with a new turbine on top, which gave a little bit better aerodynamics. And the OC5 project is presently using that data set from 2013, and we're hoping that that's getting out to at least a lot of the modelers out there, and potentially, we're hoping we can release it to more of the general public afterwards. And from a lot of these tests that we've been a part of, we've started learning some of the recommendations that we feel should be done when doing these type of tests. For tank testing, we really think the stepped approach is really beneficial. You can look at system ID type tests, wind turbine only tests, isolating the wind, wave, and currents. You should look at a variety of conditions, both benign and severe, and try to see if you can look at the influence of the controller. That's still a work in progress. Ideally, it would be great to also, if you are going to a tank test, to be able to test the turbine actually in a wind tunnel before you put in the tank. The wind quality in a tank is not that good, and you're never going to get really the great measurements that you get in a wind tunnel. So if you really can understand the turbine before you go into a coupled sense within the wave tank, that would be beneficial. As I said, the quality of wind isn't always great in the tank. The Deep Sea Wind Project did a lot of great work in building up a filter and a nozzle to try to get straight and less turbulent wind. And so that's important to have. And it's also important to be able to have repeatability in your wind and wave conditions. And one of the great things then is a tank, you can actually have all those conditions without the structure present and measure that. Such that then when you put the structure in, you can have an unaffected wind wave excitation measurement that you can use. And there's also a lot of people looking at hybrid approaches now. So we want to look at the coupled nature, but you can approximate the coupling through by doing just part of the system and affecting the other part of the system in some manner. So a lot of people have started to use just the substructure and put a fan on top or a pulley system to approximate the performance of the wind turbine. And then there's some other people now, like the people down at Polytech in Italy, that are instead going to a wind tunnel and getting rid of the waves and substructure and basically putting a base excitation of that wind turbine to approximate how the system is performing, would perform in the waves. And that's actually being done in a loop process using a wind modeling tool, a tool such as FAST that's being able to model that hydrodynamic load. Okay, so another approach to obtaining data for validation is to look at the full system in the open ocean. And the advantages of this, it's best for examining the loads and performance at an integrated system level. You have realistic wind and waves. We have the tank and we have these kind of simplistic wind and waves that go in the open ocean, and it's all of a sudden, it's very different, this whole 3D wind wave excitation that's very complex. The disadvantages, though, of course, are cost. I mean, it's really expensive to build a full-scale system. These complex mid-ocean conditions are really hard to measure and really hard to model. You're limited to what occurs naturally, so you might not ever get the extreme conditions that you want to really test the ability for your system to address those extreme conditions. You can't isolate the wind and waves easily. There may be in some locations the ability where the wind is dead and you still have waves, but that's not always going to happen. And as we've been mentioning, it's difficult to actually get all the information you need to model these systems because there tends to be IP issues now when you get to a full-scale system. So data availability, there's the Highwind, there's the WindFlute, the Fukushima project. They're all open out there. They're all running out there. People have been using the data to do validation with, but unfortunately it's not open to the public, and as we've seen, because of IP issues, it's going to be very difficult to ever make it so. So one way to alleviate some of the problems of full-scale open ocean testing is to go to intermediate scale. It's more economic that way. easier to capture extreme events because your system is small compared to the environment. You can also use a commercial turbine, which we've seen with the Volturnus system that they've tested at 1/8 scale. And you can actually have an effective control system there. The disadvantage is that you might encounter too severe of a condition because you have a scaled system, so you have to worry about that. And you still do have some scaling issues that are present. So in terms of data, we have the Sway and the Volturnus, and once again, there's been validation activities, but it still suffers from the issues with the full scale that data is just not really going to be open to the public. And just a few recommendations for open ocean testing. You have to, for scaled models in the open ocean, you're going to have to scale the system, and at times people have to scale one part of the system at a different scale than the other part just to be able to withstand the increased loading on the waves or something like that. And that should be considered because if you're not scaling the whole system at the same scale, then you're not going to get the true coupled behavior of the system. We really need redundant measurements in the field. As I've seen for any field test, lots of the sensors fail. You never get enough of the measurements, and really to understand uncertainty and really get a good sense of what's happening, you need redundant measurements. The other area that's lacking is the mid-ocean conditions. As I said, they're very complex, and people are just doing single point measurements of what these mid-ocean conditions are, and they're not really capturing the quality of what they are. We need a lot more different types of, we need a lot of mid-ocean measurements, we need different types. For wind, we need to have, floating met mast, or we need a combination of a LiDAR and an anemometer at different points. For waves, we really need the time varying measurement rather than an average over 20 minutes, and we need to know what the direction is. And we also need to capture the current, which a lot of people are ignoring. So the OC5 project is a project that's really trying to move forward with this validation of offshore wind modeling tools, and we have been approaching it kind of at this 3 different types of testing level. We started with component level tests of a cylinder and a tank, and then we're moving to the deep sea wind floating scale testing, and then we're hoping to move to this open ocean test validation, and we're working with Alpha Ventus right now, and it sounds like we'll be able to get a lot of the information from them, but it will be going through the procedure of approximating the turbine properties, approximating the controller. So we'll go through this as a group and see how well we can do validation with these approximations. But the things that have been really limiting, and I think I've been pointing them out before, is if you're trying to do validation with a pre-existing data set, it's not ideal. It's really great to have this validation group involved from the beginning and being able to perform their own tests so you can control the objectives, so you can do uncertainty assessment better. Also, just being involved in the test, you have a much more intimate knowledge of the data and testing, and you have a better feel for the data you're working with. So just to summarize, there's been some data available for offshore wind validation at component level and model scale, open to the public, but really nothing at full scale. What we really need is more public data sets. And with these data sets, we'd like the validation group to be involved with the testing from beginning to end. We want clear objectives for the test and assurance they are met. We'd like a combination of component level, model scale, and full intermediate scale data. We need high quality data. We need a focus on assessing and minimizing uncertainty from the start. We need those data and models to be open to the general public so we can see how a lot of different modeling tools compare to that data. We need knowledge of the turbine properties and controller, and we need a good characterization of the mid-ocean conditions using multiple methods. And it'd be great if we ever achieve this type of data set out there, if we ever could as a group create such a data set and as a group do some validation, which maybe we can call it OC6. I don't know what the C would be, but something out there with a C in it. So really, I think these data sets are the things that are needed to do this validation, and this is what's going to really help us advance the capabilities of these tools so that we know they're representing offshore wind systems effectively, and will help to drive the innovation of the next generation of floating wind turbines. Thanks. Well, I think the great thing that the OC3 and OC4 projects have done is, you know, every time we start out with a new system, all the results are all over the map. You look at, you compare, okay, this simulation to this simulation, there's like no comparison. They're completely different. So, and over time, we've basically converged and converged to the point where we have differences, but we understand what the differences are. There's differences in the modeling approaches of one tool to another. But I think through this process, we've gotten to know the tools very well, understand how they compare, understand what they're able to do. But, you know, until you've done the validation, you can't really say how well are we at being able to predict how this system is really going to respond. And I think we've just started on the validation side. So I think we still have a ways to go with validation before we can really say how good these tools are.
Okay. Just quick question. Predicting the motions, accelerations at the nacelle level are some of the most important things that we worry about. Mm-hmm. Are we 5% off? Are we 50% off? Ask it that way.
Again, I'd say that's really hard to say at this point. I think I'm pretty confident that I'm pretty confident in the tools, and I don't think they're very far off. But like I said, I mean, in an open ocean condition, it's really hard to understand what's exciting your system and how well it's responding until you can get these measurements to where they need to be. And so I don't think the tools are far off. I think they're close, but you know, if you really want to innovate and close that gap so that you're decreasing cost, you're going to have to be able to get to that level of detail, and it's going to require a lot of information to get there.
Thanks.
So we're working with OC5. We're working on the tank testing of the deep sea wind semi, not the Aquaventus. So it's not the same system, but it is a valid floating semi system with appropriate responses, and so it's going to be very beneficial for validation.
Well,
Jason, did you? No.
I was just going to comment on that. I think we can get you 5% with, but that requires right now calibration. You did some validation there.
Yeah, I forgot to point that out, yeah.
So I think what Amy's talking about is core to what you're trying to achieve.
Sure, Thanks, Jason. Thank you. Thanks, Amy.